On a previous video, we talked about how we could use an integral to show that the harmonic series diverged. And now we're going to expand this idea through the integral test. So it's not only the harmonic series that can be shown to diverge through the integral test, and even convergent series can be treated through the integral test. So let's ignore these 3 bullet points here for a while, and let's understand what this is saying right here. So what this is saying is that if you integrate a certain function from 1 to infinity and that integral converges, so if you remember from calculus 2, to say that an integral converges, that's something that we say when we're talking about improper integrals, so integrals that go to infinity in either direction. To say that it converges is to say that this is a number. This exists. I can calculate it, and that it isn't some negative infinity or positive infinity or whatever, right? We're saying that if this integral converges, then the series converges. And if this integral diverges, meaning that it is infinity or that it's not a definite number, then the series diverges. What's this function that we're integrating? It's the function that you'd get by replacing n with x in your series. So whatever you're adding, replace that the n's with x and integrate that. And if that converges as an integral, then it will converge as a series as well. If it diverges as an integral, it will diverge as a series. Now let's go back to the 3 bullet points that we ignored. You have to be careful with 3 conditions. So why is it that these 2 statements that I said before are true? Why are these 2 things true? Because of a sketch that I showed you last time in the harmonic series video. And I think that maybe we had talked about the test for divergence, and I showed you the harmonic series as an example that limit equals 0 is not enough, right? So when you have, let's say I have 1, 2, 3, 4, 5, and then you have some function that goes down like this. The integral of this function, so if this blue graph is y equals f of x, the integral of this function is integral f of x dx from 1 to infinity. This integral is this sort of blue area here, yes? On the other hand, f of 1 is this height right here at 1 in green. And it's also the area of this rectangle. Yes, it is the area of this rectangle. F of 2 is the area of this rectangle. F of 3 is the area of this rectangle, So when you add them all together, then this gives you a series. And from this sketch, you can see that this integral right here is less than the sum of f of n, maybe n equals 1 to infinity, but then that's what I'm calling a n, right? So if this guy happens to be infinity, so that's this bullet point, then this right hand side, it's even bigger, so it's also infinity. So that is one of the bullet points. The other bullet point is similar, and you can think of it as approximating the integral slightly differently, pretty similarly, but slightly differently. So let me just draw my integral again, my function again. So if this is 1, 2, 3, 4, 5, 6, and now I'm trying to see what's f of 1? It's this height, but it's also the area of this rectangle. I'm drawing it to the left now. Yeah. And this area is f of 1, this area is f of 2, this area is f of 3. As long as it touches the graph right here, right? So I don't want to have this extra air here. So when I add them all up, you can see, right? You can see this. This is f of 4 right here. So this second sketch of mine shows you that the integral, as long as it exists like this, yes, that the integral from 0 to infinity, the integrals from 0 to infinity is greater than the sum now, the green sum. Okay, so if this thing happens to be a finite number, then there's no way this is going to be infinity, because this is bigger. The left side is bigger, so this can't be infinity, right? If this is finite, then this also needs to be finite, because the left side is bigger. This is the idea of the integral test. There are some issues that you can have. For example, maybe your function isn't as simple as this. Maybe it goes all the way up, okay, like 1 over x. But that doesn't matter, because if that's the case, if that's the problem, then we can skip a beat and just compare these two. We'll start one step later. You see that I changed 0 to 1, and then I changed 1 to 2 here, right? So I compared these only, this area only, and then sure, I forgot one term on this side, but it doesn't matter, just add one more term. Adding one term or forgetting one term doesn't change whether something is finite or infinite, so that doesn't matter. We're not going to be changing this for the integral test most of the time. We're always going to be using integrals from 1 to infinity. The sketches that I included now are only, they're only for you to understand the idea. Also, there's a mistake here. This is supposed to be an open interval. And of course, for all of this reasoning to apply, your function, first of all, needs to be positive, because if you allow your function to go beneath the x-axis, then we cannot say anything about areas anymore, because the areas are going to be changing signs. So you don't want that to happen. You want to have this sort of squeeze limit effect, where your function is sort of squeezing your series between the x-axis and its graph. So you can't really have the function change signs, become positive or negative. Also, your function needs to be continuous. This is important, so we're going to have to check each of those, because you don't want your function jumping. And let's say you have a very neat function that you'd like to think about with this test, but then unfortunately the holes of the function, if it's not continuous, happen exactly at the integers. Let's say maybe these are all holes, and then you have sort of the correct way to fill in the holes would give you something weird. This is f of 1, this is f of 2, this is f of 3. So the series itself, the points, they will diverge. You can see this is going to infinity. So just by the test for divergence, this diverges, because the red dots are the terms of the series that you're adding. But the integral, like the area, this is a finite area, right? This point being here or not doesn't change the area. So you don't want to have this sort of weird thing happen on your integral. So you need it to be continuous. the function is. And of course you need to be decreasing. Yeah, it needs to be decreasing, because if you have something like this going up and down, up and down, up and down, all of the estimates that we just said don't work anymore, because maybe you have right here a rectangle that is a little bit above and then the next one is below. So which one is bigger? And the next one is above, maybe the next one is below or something. So you can't really tell whether the function is bigger or the sum of the areas of the rectangles is bigger. So you want to keep your function, decreasing always. And we always need to check all three of these conditions. So I'm going to solve a few examples with you today, and hopefully you'll understand how this applies. This is a very interesting, very, very interesting and very powerful test. Okay, so let's apply the integral test to a few series. So I have 5 examples here. Here's this first one. Okay, A is this guy. Let's solve A first. So how do I get my f of x? Right? I just get, let me maybe hide the other ones. I'm going to talk just about A for a while. How do I get my f of x? F of x is whatever function you get by replacing n with x. So is f continuous? Right? F is continuous everywhere except at 3. Okay, but that's fine because the series starts at 4. See, in the theorem, the series, the integral was from 1 to infinity, but because my series now starts at 4, my integral will be from 4 to infinity and not from 1 to infinity. And so how do I make sure that this is continuous? I can just say a few words. I can say f is a rational function. So I'll say f is rational. So it is continuous in its domain. That's something that rational functions are. All rational functions are continuous in their domains. And that domain includes the interval that we need, which is 4 to infinity. Because that's where we're summing the terms. We're adding the terms from 4 to infinity. Okay, so that's the first bullet point. F is continuous where we need it to be. Second condition that we need is that f is positive. So maybe I'm going the wrong order. So I did continuous first. We can do positive next. F is clearly positive. That's obvious. F is clearly positive because you're squaring something here at the bottom. Even if you weren't, n is always more than 4. So n minus 3 is positive. And so 1 divided by that thing is going to remain positive. So f is clearly positive, right? I'm looking at this too. The third bullet point, which is decreasing, is important. And so you have to argue it sometimes. You have to argue it sometimes. Is it true that this function is decreasing? This is clearly decreasing. The bottom of the fraction as n grows is getting bigger and bigger. So you can clearly prove that it's decreasing. Just say a few words. And I'll maybe say that the denominator grows with n. As n grows, the denominator gets bigger, which means 1 over bigger gets smaller, right? So that means the integral test applies. Whenever I'm using the integral test, I have to check that it applies because sometimes it won't, and that's a little frustrating. So you have to make sure that you are allowed to use the test so that nothing incorrect is concluded at the end. Because maybe the test doesn't even apply, you're going to use something. Like if you have a triangle that's kind of weird, like, I don't know, a triangle that's 7, 9, and I don't know, 10 or something. Is that possible? I don't even know if that's possible. But can you use the Pythagorean theorem here? Can you just go straight and say, oh, 10 squared equals 9 squared plus 7 squared? No, right? This isn't true. And the reason why it isn't true is because this is not a right triangle. The Pythagorean theorem only applies if you have a right triangle. And so before you start writing the Pythagorean theorem, you got to say, is this a right triangle? Is there a 90-degree angle somewhere? Otherwise, nothing applies. Yeah. So that's what we're doing here with these conditions. So this is not true. But here we checked the conditions. So we're basically saying, yes, this is a right triangle. So our Pythagorean theorem applies. So yes, this is a function that satisfies the three conditions. So yes, the integral test applies. Okay. And now how do we do it? We just do the integral. The integral from 4 to infinity of 1 over x minus 3 squared dx. I'll make a u sub. I'll make u equals x minus 3. du is just dx that way. So this becomes the integral u negative 2 du like that, because it's 1 over u squared. And then that will be from, I'm not going to change the limits of integration. I'll keep it from a to b like this. Then I'll change it back. And then this will be, I add 1 to the power. Minus 2 plus 1 is minus 1, divided by negative 1, and evaluate from a to b. But then I can go back to 4 and infinity if I change back to x. So that means I have negative 1 over x minus 3 squared. No squared anymore, just x minus 3, evaluated from from 4 to infinity. So as I take a limit, so it will be this. It's the limit of this when x goes to infinity. Plugging in infinity is this, right? It's basically taking a limit. That's what plugging in infinity means with an improper integral, minus plugging in 4. So what will I say? As I calculate this limit, this is going to be 1 over infinity. So it's going to be 0 plus 1 over 1. So it's 1. It's a finite number. So that means finally that the series converges, because that's not infinity. Right? As long as I got something that is not infinity, I can conclude for sure. Not this one, but this guy here converges. It is not true, very important, that it equals 1. It is not true. Yeah, it is not equal to 1. It is not necessarily equal to 1. In fact, it's not 1. If you go back to our sketches before, you can see that there's always this little error here. Yeah, there's an error here. There's an error here. There's an error here. So the 1 is the blue area. It's the integral I calculated on this sketch. And so it's a little less than the actual sum of the series. Okay? So the sum of the series is actually a little bit bigger than 1. But it still exists. It's still finite. Okay? So I hope this makes sense. Let me do a few more examples. I think that makes sense. I'll do this one. Okay, skip this guy. Give myself a little space to work on this. See, this is very different from all other examples of series that we've seen before. But also, if you look at it for a little bit, you can sort of see that you know how to, if you replace n with x, you kind of know how to integrate this. And so that's what you do. You start with, that's a tell for the integral test. If you see something inside of the series that looks integrable, you know or have an idea of how to integrate it, then that is a possible candidate for you to use the integral test on. This is why we study this after calculus 2, so that you know how to use integrals here. So I'm going to take f of x equals arctangent x over x squared plus 1. So f is increasing. First, f is positive. I need this. Is f really positive? We've got to think about it, right? The bottom is always positive, and so that's fine. just the top needs to be positive also. And if you think about arctangents, if you remember, talking about positive tangents, what's the range of arctangents? Meaning, when I plug a value into arctangents, right, what angles does it spit back? So when I look at it like this, it should be this right half. The range is negative pi over 2 to pi over 2, meaning it is possible that we would get negative angles on this interval, but we would only get those if the tangents were negative. So if you remember, all students take calculus here, all three basic trig functions are positive, so that includes tangent. So here tangent is positive, but here only cosine is positive, which means tangent is negative. So there's no way that by plugging some n in, I would get an angle here, a negative pi over 2 to 0, because for that to happen, that guy would have to have negative tangent, and I'm calculating the arctangent of a natural number, and natural numbers are positive, okay? So whatever I'm getting, arctangent, these numbers here on the top, maybe that was a little bit of a convoluted explanation, but these angles here are on this first quadrant. Arctangent of n for n natural only live in the first quadrant. And so, all right, so that's all just to say that f is positive. Second is f continuous. Yes, f is continuous. You have to say it, even though it seems obvious. N squared plus 1 is never 0, so there's no asymptote issue. And the arctangent is also continuous. As n goes to infinity, doesn't really matter. The range needs to be this, but the domain of the arctangent is all real numbers. Okay. So if it is continuous, everything's fine. And now we need to find whether f is decreasing. How do I prove that this guy is decreasing, right? It's kind of hard. It's not as obvious as before. So here's what I'll do. You're not going to like it. I'm going to take its derivative, this, and that requires me to use the quotient rule. So it's the derivative of the first times the second minus the first times the derivative of the second. Doing it wrong. Derivative of the first is the derivative of the arctangent, is this. That's correct. Times the second is just this. So it's just x squared plus 1, like this. And then the first is just arctangent times the derivative of the second, and that's 2x. All of that divided by the second squared. And so these cancel. I get 1 minus 2 x arctangent x divided by x squared plus 1. And so that will be, let me move this out of the way. That will be this. So I want to see if this is decreasing. That's the reason why I'm talking about this. And I know this is decreasing because can I say that this is negative at some point? Whenever the derivative is negative, I can say that something is decreasing. In fact, the bottom squared, I forgot to square the bottom. The bottom squared is always going to be positive, but the top, 1 minus 2x, is going to be negative sometimes. This is less than 0. So when will this be negative, right? When will this ever be negative? Yeah, difficult, huh? Move this over to the other side. Can I ever get this? Can I ever get this? No. Difficult. But you can think about what happens to these values as x grows. Because if you go back, x is playing the role of n, and n is going from 1 to infinity. So even though at 1 maybe this isn't true, at exactly 1, at some point it needs to be. Maybe it isn't true at 1, maybe it is, I don't know. But will it happen when x grows? When x goes to infinity, 2x over arctangent x is what? As x grows, this is going to go to pi over 2, the arctangent of infinity, right? And this is going to go to infinity. So it's 2 times infinity times pi over 2, basically. It's going to get bigger and bigger and bigger, so this limit is infinity, which means this guy will get super big for certain values of x. As x grows, this guy grows as well, which means at some point it's going to be bigger than 1. Of course, if it goes to infinity, it's got to be bigger than 1 at some point. And then this will also be negative, which will mean that this is negative, which will mean that the derivative is negative, which means that the function is decreasing. So I can finally say, all of this is just to say that I can use the integral test. I can say f of x is eventually decreasing. Even though I don't know for sure that it's decreasing immediately, I don't really care. It is going to be decreasing at some point for a large enough x. Hope that makes sense. This is the third bullet point in me checking the conditions for the integral test. And I'm now going to just go ahead and apply it. So I have to solve an integral. Let me get this out of the way as well. Did not budget my space very carefully. So I'm going to say this. I'm going to say the integral of f of x dx, and that's from 1 to infinity. I'm going to calculate it. If I get a number, then that means the series itself converges. And if I don't get a number, the series itself diverges. But that's not bad. I can make a u sub here too. This is u, which makes du equals 1 over x squared plus 1 dx. So this will then be the integral of u du. Right, all of this becomes du right here. And so I'm not going to mess with the limits of integration. I'll leave them be. But then this becomes u squared over 2 from a to b. Then I'm going to change them back to move this one last time, and then I'll have space. Okay. And u was arctangent, so this is arctangent x squared over 2 from 1 to infinity. So then I got to plug in infinity, and that means take a limit. And then minus, plug in 1, and that just means plug in 1 as a number. So finally, as I've said, as x goes to infinity, this is pi over 2 squared over 2. And then the arctangent of 1 is an angle whose tangent is 1 in that interval that we talked about in the range of arctangent. And so that will be pi over 4. Do I care about simplifying this? No, I do not care about what this is. All that I need is to be able to use the integral test, and all it asks for is that this is a number. As long as it's not infinity, I'm good. So I can say this, and so the series converges. And I'm done. It's a little bit of work. It's a little long, but the ideas are all there. have 3 more examples, but this video is getting a little long, so I'm not going to solve them. I'm going to leave them here on the screen for you. But I'll tell you the answers. I'll say this. You always have to check the 3 conditions. And based on the phrasing of the problem, the only thing you're supposed to do is just use the integral test. If you use the integral test here, you're going to see that this one diverges. If you try and use the integral test here, you're going to see that the integral test does not apply. This is not going to be increasing. It's going to be switching sides. It's not going to be all positive either. So the integral test does not apply on this one. And on this last one actually, I think it converges. Okay. I think you can use an integration by parts. Integrate by parts. But again, you have to check all 3 conditions. That it's positive, decreasing, and continuous. Okay? So go ahead and try those yourself. I'm going to stop this video right here.